Hey, it's Kathy Deeks, and I'm gonna give you this presentation on how tubulin is used in cell division, and then how this Oncovin binds to the tubulin and leads to the prevention of cell division. I think I've worked enough times to figure out how to get this slideshow to show while I'm giving this presentation. So I guess you can't see me for the minute or a few minutes that I go through this presentation, but then I'll put myself back on. All right, so during the mitotic or M phase, the microtubules align the chromosomes on the metaphase plate and separate the chromosomes during anaphase. So just a review of that cell cycle. And all the needed proteins are made during that interphase in G1 and G2. But if there are missing resources like proteins, enzymes, or ATP, the cell cycle ceases at a couple of different checkpoints, which we know is the G1 just before going into the S phase, or the G2 just before going into the M phase. This is a picture of a microtubule. The assembly is regulated by the GTP-GDP ratio, where the GTP is bound tubulins tend to assemble, and the GDP bound tubulin tends to disassemble. I mean, those are the two different states. The proteins exchange the GTP with GDP using GTP exchange factors, but when GTP bound tubulin binds to the growing microtubule, GTP is hydrolyzed. Tubulins are targets for anti-cancer drugs like the vinca alkaloid, vincristine, or Oncovin that we're going to be looking at. And let's see. Okay, here is just one of those pictures that showed the microscopic or view of the tubulin, and the positive end is where the GTP tubulin polymerizes, and the negative end is where the GDP tubulin depolymerizes. And if the assembly rate of the microtubule is higher than the rate of hydrolysis of GTP, then it's formed this is where the polymerization is going to occur. If hydrolysis rate is faster than the assembly rate, then the GDP is formed, and that leads to disassembly of the microtubule at the plus end. Here's another picture. It's an older picture, but it just shows better the mitotic spindle and the bipolar array of microtubules. There's intrinsic polarity where the beta tubulin face positive end and the alpha tubulin face the negative end. And so the microtubule is made up of these alpha and beta tubulin heterodimers that associate their head and tail and lateral form hollow filaments. And it's very dynamic in stability. The ends switch between growing and shrinking, and that's what is key for the use of how this mechanism of this drug works that we're going to be talking about. The microtubules are modified by post-translational modifications. A couple of the studies that I looked at, because of course I get carried away in reading about things, and so I will just say a sentence or two about some of the things I was reading about. There's different isotypes that can contribute or combine into the mosaic microtubules with specific chemical properties that translate into specific functions. The polymerization of microtubules occurs by nucleation and elongation mechanism. And so I was reading in one of the studies about this detyrosination that distributes among the microtubule and creates the spindle, and that regulates kinesin 1 and 2 processing and reduces depolymerization activity of kinesin 13. And scientists have identified detyrosination inhibitors, so the reduction of detyrosinated tubulin won't occur. Modulating the tyrosination-detyrosination cycle seems to be a key player or inhibitor in the anti-cancer properties in apoptosis, DNA methylation, P21 signaling, and the INF alpha regulation. Let's see, another thing that I read about and got carried away in one of my research articles was about this force that efforts to measure forces generated within the microtubule networks by assemblies of key proteins have been studied, and there's this length-dependent force generation protein clustered by asymmetric friction and entropic expansion forces. And studies of that specific force or forces have helped scientists understand the force generation needed for spindle function and integrity. And it was found that the spindle can produce a significant mechanical work by exerting forces on the micron length scale. They compared to the tiny bit required to move the chromosome. So it was, question, how can the spindle maintain its structure of a microtubule and not collapse under this extreme tension? And it was found that microtubules that fill the spindle but do not interact directly with kinetochores are making opposite forces. So there's a balance of this force occurring, and so they work in a steady state. And I found that very interesting. There's also some passive forces, but it was this other one that was more responsible for what we're looking at. Then of course I get sidetracked, but it's sort of interesting to learn about how this drug was found, of course, in our heritage, our ancestors. We know majority of drugs come from the rainforest, the plants and the ecosystem and stuff. And this periwinkle plant was found only in Madagascar. And then in the 1700s, it was brought to Europe, and then 1800s throughout all the tropics in Europe. It was used for things like infant eye wash, gargle for sore throats. It was used for wasp stings, malaria. There was periwinkle tea that was used for diabetes. They learned later on that really was just more of a folk cure. And then eventually it got all over into the United States, and anti-cancer properties were discovered by accident. These guys in Canada were lucky enough to stay late at some conference and learn about it. And then it was, of course, the Eli Lilly company that took it and ran with what they could find. Okay, now this is a pathetic picture that I just could not properly upload, but this is really the heart of what my presentation is going to summarize here, in that we have this dynamic behavior, dynamic instability, where microtubule ends are switching between growth and shortening phases. And they're inequivalent ends. The positive end grows and and shortens faster than the negative end. If there's no growth nor shortening happening on the microtubule, we'll have long periods of slow lengthening and short periods of fast shortenings, or and then we'll have these pause periods. There's the second dynamic behavior is this treadmilling, and that is the net growth at one end of the microtubule and balanced by the net shortening at the other end. And so there's this intrinsic flow of tubulin subunits from positive to negative end caused by subunit concentrations. And this is what is very, very important. The timing for the chromosome attachments at the kinetochores. And so the Oncovin medication that we're looking at here blocks that mitosis. It inhibits cancer cell proliferation because it suppresses that dynamic microtubule function and kills the tumor cells. It does this because cancer cells are sensitive to these compared to normal cells, because the cancer cells divide faster than normal cells, and they pass through a stage of vulnerability to mitotic poisons. And these drugs act on the polymerization dynamics of the spindles. They are anti-mitotic agents that inhibit cell proliferation. So Oncovin is a microtubule destabilizing agent in that it inhibits microtubule polymerization at high concentrations. There are also stabilizing drugs that stimulate microtubule polymerization, but this one that we're looking at is a destabilizer. Thus, it's a powerful suppressing microtubule dynamic at 10 to 100-fold lower concentrations without changing the microtubule polymer mass. The most important thing is the suppression of the spindle microtubule dynamics. It slows or blocks mitosis at metaphase and anaphase transition and induction of apoptotic cell death, rather than affect the microtubule polymer mass. Oncovin binds to the beta tubulin subunit and has clinical uses in leukemia and lymphomas. The drug binding site is adjacent to exchangeable GTP binding site in the beta tubulin at the plus end. Okay. Let's see if I'm still on here. Yep, and that was... Oh, great. Looks like it didn't even record, but...